Hello, everyone. Welcome to Power Up Asia panel discussion. I am Maurizio, editor-in-chief of powerelectronicsnews.com, and today we will talk about advances and challenges for wide bandgap semiconductors. I have the pleasure to discuss this topic with great speakers. So let me introduce the speakers. Francesco Muggeri, Vice President of Marketing and Applications, Power Discrete and Analog APEC China at ST Microelectronics. Hi, Francesco. Thanks a lot for being here. Stephen Coates, General Manager, Asia and Vice President of Global Operation at GaN Systems. Hi, Stephen. Welcome aboard.
Hello, everyone.
Andrea Bricconi, CCO at Cambridge GaN Devices. Hi, Andrea. Thanks a lot for being here.
Hello, thanks for having me.
Amitava Das, co-founder and COO at Tagore Technology. Hi, Amitava. Thanks a lot for being here. Pete Losey, Director of Technology Development at Corvo. Hi, Pete. Thank you for being here. And Thierry Boucher, CEO of Vice Integration. Hi, Thierry. Thank you.
Hi, Maurizio. Thank you for the invitation.
Okay, so during this panel discussion, we will talk different topics. So I have 3 topics to share with you. So please stay on schedule, on time, a few minutes for each one per topic. So let's start with the first one. So we will try to analyze which are the challenges in terms of wide bandgap. So silicon carbide in particular and gallium nitride technologies. So they are continuing to emerge in the market. Companies are expanding the solutions, are developing to offer an extensive portfolio of devices. In these last years, the ecosystem of wide bandgap has been characterized by development and growing industry acceptance. If you talk about reliability, this is the next topic. So let's explore the prospects of both materials, gallium nitride and silicon carbide, in multiple application contexts from your point of view. And so which are your contribution to the industry from each of you, each company? We can start from Francesco, ST Microelectronics, and then we can follow the order that I said earlier. Francesco.
First of all, I thank you for inviting me on this special panel here to discuss this important investment that all those companies here online are making for developing new technologies like silicon carbide and gallium nitride in particular. Let's say what is important for us, at least in ST, is to differentiate this market. So, as you know, silicon carbide is already a big reality for us, and we have extensively gaining market share in the past year. Somehow, we are proud in ST to be the initiator of the big, let's say, growth in silicon carbide, particularly for traction inverter applications. And on this, our technology, our planar technology, has been a great success. Now, if we go more in details on what we are doing, our preferences went through to address the automotive market. And as such, we have been focusing on traction inverter, as I mentioned before, and we had a technology advantage. And it was clearly on the capability of the device to not change the RDS(on) with a variation of temperature. So this was a major topic. Anyhow, still many challenges are there. We are innovating, we are generating new technologies, and this is in a learning curve together with our customers. And when we go in the market, now we are differentiating, we are taking the industrial segment as well, and we are very strong. This is something that is not reflected on gallium nitride from our side. The gallium nitride is a more complex technology. Somehow is limited to a planar as well overall, while in silicon carbide there is some visibility of trench, and our competitors are mostly on trench technology. We are still, let's say, with the gallium nitride to a 650 volts technology, and we are addressing both, let's say, the power and the system in package. As you know, the technology allow to faster commutation. Therefore, operating frequencies can go above, let's say, 400 kilohertz, that close to the megahertz, and this require particular topologies. In particular, requires special needs for, let's say, system in package. System in package facilitate the adoption of the devices. And on this, we are already in the market with Master GaN and what we call Viper GaN. So a double switch with gate driver and half bridge topology, and the Viper GaN, which is nothing more than a controller with a switch in a flyback topology. With this, we are in the market. We have been successful, and we keep investing on our side and for producing with the internal technologies.
Thank you, Francesco. Stephen Coates, GaN Systems.
So thank you so much for the opportunity to be here today. Let me see if I can share my slide here just for a moment. I think, as you mentioned, we're really seeing GaN adoption tremendously widening. So 100 times better performance in GaN than silicon IGBTs, for example. 5 times better than silicon carbide. With a very highly proven performance, what we're seeing delivered is higher efficiency, smaller size, lower cost. And in parallel with that, a process which really is based upon very mature silicon manufacturing processes, GaN on silicon, widely used in many consumer products today. That means there's abundant capacity. That's driving prices to fall ahead of forecasters' predictions. And we're seeing price performance beating silicon. So let's spend a moment thinking about some of those applications that are really taking full advantage of GaN today. So in the data center, where profitability is important and sustainability is important, we're really seeing that GaN is helping to drive both of those initiatives, and that's really budging the needle fast on GaN adoption. We all know that there are stricter regulations for energy utilization, new industry standards for power supply efficiency, form factors, 80+ titanium, and so on. Open compute, asks for a 30% volume shrink, and more data. More data drives increasing computing power, rising energy consumption, and GaN-based power supplies not only help deliver, of course, lower emissions and better energy efficiency, but $3 million per year per 10 rack set in terms of pure profitability by having more servers in the rack and less power supplies. And GaN-based power supplies really meet that 80+ titanium efficiency requirement while achieving power densities above 80 watts per cubic inch. So that's a big deal when it comes to data center. Of course, in automotive, e-mobility, passenger cars, buses, all the way down to micro mobility. Here, policy supports and increases customer acceptance. That's really driving this shift in electrification in all segments for mobility. So 11 kilowatt, we're seeing 22 kilowatt onboard charger becoming mainstream. And as the previous speaker mentioned, switching frequency is really important. And the higher the frequency, the smaller the size. That gives optimized power density, improves efficiency, and takes weight and volume out of the car. In GaN Systems, we're very proud to announce recently our 800 volt GaN OBC reference design, 35% better power density, 15% lower BOM costs. And here we're taking full advantage of a multi-level GaN topology to really drive BOM costs better than silicon carbide even. And beyond that, we're seeing customers also interested in UPS and industrial areas taking advantage of this. So really, I think net, I think the adoption of GaN, it's been mainstream for a long period of time now in lower power ranges, in chargers and so on. And it's these higher power segments now that are fully taking advantage of the benefits of gallium nitride.
Thank you. Thank you, Stephen. Now, Andrea Bricconi, Andrea, Cambridge GaN Devices.
Let me share my screen. I hope you can see it.
Yes.
So Cambridge GaN Devices is a fabless GaN semiconductor vendor who spun out from Cambridge University a few years ago and is in mass production since 2022 with 650 volts transistors and ICs based on gallium nitride. Now, coming to the theme of this panel, I would like to focus on a few topics. Today, if you look at the GaN market, it is addressed by several different GaN technologies, different concepts, D mode, enhancement mode, with different level of integration. At the end, it's nothing new. Every new technology comes like this, and silicon carbide was present with planar MOSFETs, trench MOSFETs, even BJTs. And with GaN, we'll see how the market will go on, what kind of concept will be selected. We are very much focused on a significant level of integration in the GaN chip, because we think that the lateral nature of gallium nitride enables to solve specific problems or to follow up on specific opportunities at application level by selectively integrating ICs, not the full gate driver, but just different ICs that deliver different functions in the same power transistor. In doing that, I think we can also help to hit that perception that is still out there, that somehow GaN is not mature enough or is not reliable enough. I have a short example. Years back, a customer of mine involved in telecom was telling me, Andrea, when I qualify my system with very stressful tests, the first thing that somehow is killed is the silicon power MOSFET. Now with GaN, I cannot kill it. What happens is normally a passive will die, like a capacitor, but GaN transistors are unbreakable. And that is because there is not a specific reason why GaN cannot be as reliable or even more reliable than silicon carbide or silicon. It's simply a matter of time and a matter of progresses in the technology innovation. But in terms of voltage, it is heavily derated. So a 600 volt device typically has a breakdown voltage well above 1 kilovolts. And so far, the industry has demonstrated that GaN transistor can be very reliable. It's a matter of time. Perception cannot be just answered by with words, but with data. And we are all together coming with data showing that, even in the automotive industry. Differently from silicon carbide, there are plenty of foundries that are now offering quite good services and good mature processes for GaN. And that is why there is a proliferation of vendors. We are with TSMC, probably the biggest one. And that helps really to select different processes and different technologies. And I think that altogether we are come with a significant level of innovation, knowing that we are still more than one order of magnitude far from the theoretical limit of GaN. I would say that today, the adoption of gallium nitride is significant. We have a tremendous success in the consumer market, in the industrial market. Automotive is still a question mark in terms of size and when it happens, in particular because silicon carbide, thanks to the early innovators, managed to take the lead. It came first, of course, and most of the customers are still deploying a lot of resources in making sure that silicon carbide is fully utilized there. But again, GaN will come also at a 1200 volt level. It's a matter of time, but I'm pretty sure that basically, together with all my fellow competitors, we'll make it there significantly.
Thank you, Andrea. Thank you. Now, Pete Losi, Corvo. Pete.
All right, Joe, let me see if I can share my screen.
Sure. Yes.
Okay, great. So, you know, we're formerly United Silicon Carbide. We were recently acquired by Corvo. And the reason, is my full screen sharing or you're seeing the bar on top?
No, I can see your slide. Everything is good.
And the main sort of reason is that we have a somewhat differentiated technology where we use a silicon carbide JFET in a cascode configuration to make the normally off switch. And people sometimes ask, well, why cascode? Well, there's a lot of advantages and some challenges associated with a cascode, but the real sort of reason is the superior RDSA, right? So the lowest specific on resistance switch of any technology is a silicon carbide vertical JFET. And so by combining that with a silicon MOSFET, you can achieve this normally off device with the lowest or least amount of die area, right? And so if you look at the plot on the right or the left, you'll see sort of the silicon carbide JFET as the sort of baseline or the unit of one, and then the other sort of 650 or 750 volt offerings normalized to that value, right? And so a significant RDSA advantage at room temperature. More than 2x higher for the latest silicon carbide MOSFETs at 750 volts, right? And the other thing that sort of you'll notice is that the temperature dependence of that RDS-on is a bit steeper than its peers. And there's a reason for that, right? The drift mobility, the sort of bulk mobility decreases with temperature. And so if you come off of that sort of steepness, it essentially means there's something other parasitic resistance in the device that's not following that sort of bulk mobility decrease, right? And so what you see is that MOSFET evolution from Gen 3 to Gen 4 is actually steepening that TEMCO. And that just means that they're getting better and they're getting more close to the ideal sort of conduction characteristics that the silicon carbide JFETs already have. So while the temperature dependence is steeper, it's still a sizable advantage across the whole, useful operation space, right? So, lower RDSA means that you sort of shrink the die and you get advantages like lower capacitance and lower switching losses associated with that, right? Obviously, you get sort of better utilization of the substrate and presumably a better price point. But again, doing that without sort of improving thermal resistance will start to limit your thermal or power handling capability, right? And so what we have to do is we have to, in silicon carbide, as die shrink happens, you have to sort of keep beating out this thermal resistance. And so you have to go to things like advanced die thinning and reduced and sort of advanced die attach processes to give you the cycling life and thermal resistance that you need to get the most out of the chip, right? And so this sort of center figure, it's basically showing the sort of relative die size of a low on resistance FET with the sort of thermal resistance from junction to case by employing these sort of techniques, right? And so this sort of getting the most out of wide bandgap from sort of a performance entitlement and then a usability standpoint. And when you combine this, what you're seeing in silicon carbide and wide bandgap in general is that you can actually offer very low on resistance parts in very small packages, right? And so by combining that very low specific on resistance with this sort of thermal resistance advantage, you're able to get things like the TO leadless, which is a very small package with the on resistance as low as 5.4 milliohms, or a D2 pack 7 lead, still maintaining a high creepage distance as low as 9 milliohms, right? And so now you can kind of do things with discrete FETs, but we're only sort of capable with power modules in the past. And so we kind of look at sort of the continued evolution of higher performance packaging to allow this sort of iterative process of die shrink, device sort of architecture improvement, and then the packaging coming along with it.
Thank you. Thank you, Pete. And now Thierry Boucher, Vice Integration. Thierry.
Yeah, thank you, Maurizio, for the invitation. And let's share my screen. So why is integration? Why is integration? So it's the digital GaN company. So we are a fabless company. So we provide to the market GaN devices, power GaN devices. We already have on the market discrete, half-bridge, and GaN integrated device. And we also provide the digital controller. So this is what we bring to the industry. The digital controller is MCU 32 bits standalone microcontrollers, where we implemented our own firmware to replace on all the AC to DC power supply in the middle range of power, 65 to few kilowatts, the analog control. And why we do that is because it was already presented by Stephen, and also Francesco. They talk about the capability of GaN. If we want to maximize the benefit of GaN, so it means that try to push to the high frequency capability, which makes sense if we want to reduce the size, improve the bill of material of the system, and also reduce cost. It's not really possible with analog control because you have a limit in terms of switching frequency. So digital can activate this possibility. And so with this digital control, we can help our customers to accelerate the development time, because you replace at least 2 to 3 analog controls that are used for a power supply, AC to DC, with only one digital control. We also can activate, thanks to the benefits of the GaN, of the digital control, I mean the MCU capabilities, by making a small change in the topologies. We can also make a virtualization of the PFC power stage. So it means that we can accelerate the benefits of the GaN and reducing the power dissipation, and so improving the total efficiency of the system. And for sure, as we remove some physical element in the power supply, we can also improve the bill of material. So this is what WISE integration is target to bring to the market. And so we can use the digital control with another GaN device, but with our GaN device, what we provide is we integrated some function inside the GaN. It's the same strategies and what Navitas is doing, but we do it with the target to make some MCU direct drive function. It means that we introduce inside the GaN monolithically some driver inside that could be drive at 3.3 volt, which is the output voltage of the GaN. So today we penetrate the market like the competition with the high-end consumer. So we already have customer for 65 watt power supply, so USB PD solution. We also are the first company that introduced onboard charger for e-bike, so in Europe. So it's something very interesting. As we can do it very small, we can be able to promote this kind of innovation. You have the charger inside the battery, so you can charge everywhere your e-bike. And for the future, we will move, thanks to the digitalization, to more powerful solution for industry. Also, GaN system talk about data center. Also, it makes sense for sure to move in this way. And also a very interesting market for us. Thanks to the digitalization, we can make at high frequency power supply very thin. And so we can do some SMPS, for example, for monitor and for TV application. For the near, this is what we target for the next year.
Thank you. Thank you, Thierry. Okay, Amitava, tell us your perspective.
Hi, Mauricio. It's good to be here. There's a lot of activity right now on wide bandgap semiconductor, and here I have prepared a brief table to first show the comparison between the three main contenders. One is the traditional power MOS superjunction transistors. The second one is the silicon carbide and Tagore GaN. So let's first start with the comparison of the devices, and then we look into the performance for which application is suited for what type of devices. So for comparison purposes, what I have done, I have taken three very similar devices. The superjunction is around 100 milliohm, silicon carbide is around 100 milliohm, and the Tagore GaN is 90 milliohm. They're all 650 volt breakdown voltage, and actually they're 650 volt rated. So if you look at the first metric, which is R on QG, kind of normalized with R on, and you can see that superjunction has fairly large number, and of course the GaN is extremely good R on QG metric, and silicon carbide a little bit actually quite a bit worse than GaN, but much better than silicon superjunction. Next metric is QRR. The QRR actually superjunction is very bad, as you can see, and there are some version of superjunction where the QRR is a little bit better than what I have quoted here. But for continuity, I kept the same device. Here we see the silicon carbide is significantly better QRR, like a reverse recovery charge, whereas in GaN there is no reverse recovery charge, is close to zero. The next metric is EOSS, and here surprisingly, and it's kind of well known that the way the superjunction is architected, the EOSS is pretty good and is fairly comparable to GaN and silicon carbide. All three are approximately the same. Now coming back to the last metric, which is R on QoSS, you can see again similar behavior as QG, is that silicon MOS is significantly more charged compared to silicon carbide, and silicon carbide and GaN is more or less same, with GaN slightly better. So this is the landscape in terms of the various parameters. Now let us see how this translate to various applications, because at the end of the day, you have to really look at each application and then decide what is best suited for them. So let's start with the mid power range, and they're typically two blocks, right? You have the PFC block and then the DC-DC block. So in the PFC block, one very interesting trend is to use totem pole PFC. Essentially, you get rid of the rectifier bridge, and you can use this totem pole PFC. And unfortunately, for because of the large QRR, you cannot use a superjunction MOSFET for totem pole PFC. Your only choice is either silicon carbide or GaN. So this is a very important area where wide bandgap material will excel in the totem pole PFC, and this is the path to really hitting the 99% peak PFC efficiency. Now between GaN and silicon carbide in totem pole PFC, there's really GaN comes up with a slightly better performance in terms of the efficiency, but silicon carbide has much less temperature variation of RDS on. So that's a little bit easier to optimize for varying loads. But again, I want to stress that this totem pole PFC, you need wide bandgap material for that. Now, compared to the traditional boost PFC, you can see that, and that's more driven by the EOSS metric. You can see that superjunction or GAN both are okay for traditional boost PFC, where basically GAN might give you a little bit better performance, but superjunction will be much cheaper. So I would say that's either wash or superjunction is probably the right choice for boost PFC. In the LLC, which is a part of the DC-DC, if you look at the various metrics that I listed above, you will see that that the QG and QoSS in GAN is much better, and we feel that GAN can provide the best performance in the LLC, where you have the soft switching and followed by silicon carbide. Also, if we can have magnetics which can support higher frequency, GAN will outshine all other technology by providing higher power density. So GAN will provide highest power density in LLC at this point, but as the magnetics improve and we switch at even higher frequency, then GAN will certainly be even better. Now, in terms of the low power, for example, power adapters, like let's say 45 watt, 65 watt, and there the topology is QRF or active clamp, and in that domain, in our opinion, is GAN enables high switching frequency. For example, you can switch up to like 400 megahertz, 500 megahertz. Again, it all depends on the magnetics, and you can achieve very high frequency, very high power density. So in the low power adapter area, we feel that GAN will slowly and surely displace superjunction MOS. So roughly, our view is that based on the performance metric of superjunction, silicon carbide, and GAN, we have to kind of look at the application and look at the performance metric, and then make the decision which works best for that particular application.
Thank you. So a lot of topics to talk. So and some of you also mentioned reliability. Maybe we can understand better this topic. So I talked a few weeks ago with some of you at PSIM about this topic, reliability. So concerns about reliability are not new in the industry. So they have been growing now recently as the advanced semiconductor content is increasing, is continuing to rise the application in several markets, in critical applications. So the choice when you are so I try to put on the table the second topic, and then I would like to have from each of you a comment. So the choice of devices in terms of gallium nitride, in terms of silicon carbide, could depend on reliability, performance, cost, of course, and so on. So how do we assess do you assess quality and reliability? So talking about reliability means the physics of the device. Talking about quality, that means how many parts per billion would fail. That is important. GaN and SiC are newer technology, and so before using them, customers may want to gain a deeper understanding of the reliability issues for these technologies. So the key would be to be able to predict and prevent failures, and to define an acceptable range of operating conditions for a particular applications. So what about also applications? So in terms of automotive, which type of testing do we need to take care, talking about reliability for automotive, but not only in industrial? Which are the main failures, the main qualification test, JEDEC standard or beyond? For GaN, I can mention on resistant dynamic RDS on. Some of you mentioned, I guess, gate oxide for silicon carbide. That is still challenges, is still a challenge, I guess. So in terms of silicon carbide, but not only, bias temperature instability, bipolar degradation effect, and so on. So I know that the topic is ultra wide, is a huge topic, and but we can't stay here until tomorrow. Maybe just a short comment, a few minutes from each of you about reliability. Francesco.
Let me introduce for silicon carbide in particular something that is really for us was really something new and gave us a big gain on yield. I understand you want to talk more on the application towards the market, but I want to share another point, the point that one of the biggest challenge for this new technology is the yield. And when we talk about yield, we have if it's not clear what I mean about yield, is the number of components that put in a wafer in comparison to the total availability of potential availability of dies in the same wafer. So when we talk about silicon carbide, we have original scene that we call that's the wafer, the raw wafer, the substrate come with the defectiveness, and it's much higher than a traditional silicon wafer. And on that, we have been through several steps, because what is a nearly unseen defectiveness of the crystal, silicon carbide crystal, may evolve later on with the growing of the epitaxial layer on a big defectiveness that may extend across several dies. This is something that at the beginning was a big challenge. And later on, we were able to create a kind of mapping, early mapping, and capability to fix some of those defectiveness on the next level of epitaxial layer growth. And with this, we were able to increase significantly our yields. Typically for silicon carbide in ST, let's say I'm giving some indication in an early stage of production for a new technology. For example, at this moment we are in the market with the generation 3. With the early technology, perhaps around 1 year ago, we were with this device in an early stage of production in prototyping, and we had yields that were around 50%. That were not really something we can accept for production. And later on, we were able, thanks to this improvement I described before, on the mapping of the early defectiveness, and later on in healing such kind of defectiveness, let's say, we were able to reach yield far above 80%. This is an outstanding result for such technology. If we move instead on another critical issue that we have when we talk about yield, we have lot-to-lot yield variation. And this is another element that we were able to stabilize and get a very smooth and stable production. This is something that is a great success in our company, because this has improved the cost structure and increasing the capacity output at the same time. And this was also again a critical step once we are moving to the 8-inch. Okay, and this is from a production point of view. I think this gives a different aspect of what you asked, but is extremely important.
Thank you, Francesco. Steven, GaN Systems.
Well, thank you, Maurizio. Super important topic, obviously. Just spend a moment. I'll try and keep this high level as well. This certainly is a topic, I think, which is close to everyone's heart, and it's a topic that we could probably spend each, several hours talking about. In GaN Systems, our philosophy really has been driven from the outset. We embarked as a low RDS on, high current company, and really I think that philosophy, over the many years we've been building and testing devices, I think has really formed the cornerstone of our testing methodologies. There are structural and device physics differences between silicon devices and GaN devices. MOSFETs, typically vertical in silicon world. GaN E-mode, which is what we make in 650, 700 and 100 volt, are lateral devices. And of course, our customers expect the minimum requirements of JEDEC and ACQ in automotive to be the minimum requirements. But in fact, it's clear that the testing methodologies have to pass those minimum requirements. And how have we done that in GaN systems? Well, many ways, which I think have resulted in some of the industry's best failure and time rates. We have a fit rate of less than 0.1, which is up there with the best in class silicon devices. It's about running large sample sizes over extended periods of time. And what we've done is, in automotive as an example, we've taken our very unique Auto Qual Plus testing process, which uses JEDEC and ACQ as the baseline. And then collaboratively over many years, and remember, we started out as a high current company. So these are customers that we've worked with in automotive, industrial, data center. And by working with those customers, we've developed very specific test to failure and testing models, which are very GaN specific. And our testing durations typically were exceeding up to 27 times that of the industry standard testing duration. So we've really proven quality and reliability with some of the industry's most demanding customers, applications, automotive, industrial, high rel, and the leading consumer companies. And I think it's also important to just spend a moment thinking about it's important to deliver this transition smoothly from silicon to GaN by offering comprehensive design resources, lots of FAE and AE support. And as Francesco mentioned, yield is also super important here. It's all well and good to have comprehensive testing and screening methods, but can you deliver it with acceptable yields? And in GaN systems, I think we're very proud to be able to say that we have silicon type yields today at all current ratings. So, I think this smooth transition from silicon to GaN is really gathering momentum, and it's really across all of those segments. And every customer, demands the highest quality and reliability standards. And it's incumbent upon us all in wide bandgap to make sure that we're delivering that to the best of our abilities.
Thank you, Steve. Thanks a lot for your point. Andrea, what about reliability?
On the reliability topic, I always would like to differentiate between demonstrating reliability by testing and by design. Stephen has already discussed a lot on the JEDEC and on the fact that, of course, JEDEC was built for silicon. And so a new set of guidelines is being built now with the JEDEC 70 committee and others where we are in as CGD, because every reliability test at the end of the day has to stimulate the specific failure mode of that given technology. And GaN has additional failure modes with respect to those we are familiar with silicon. So the testing is obviously something that has to go well beyond the standard JEDEC guidelines. But we at CGD, perhaps given our background, so the two founders of CGD were basically in charge of the GaN research at Cambridge University years back, with a significant work on the reliability of wide bandgap devices. We try to tackle the reliability topic by design as well. And in fact, our direction to integrate specific ICs, not the foot gate driver, but specific ICs into the GaN transistor are having a big impact on the reliability we can guarantee to our customers. For instance, integrating a Miller clamp, which is quite an industry first in a GaN transistor, helps a lot in terms of the VDT and the IDT immunity. Integrating voltage regulators and voltage limiters, which is what makes our the gate safe operating area much wider than normal E-mode technologies, helps a lot in tackling one of the potential weaknesses of E-mode GaN, which is the gate. So normally, the GaN gates of E-mode transistors requires a gate voltage that does not exceed a certain level, like 6.5 volts, 7 volts. That is normally taken care by external driving circuitry to clamp the voltage and to ensure that the gate voltage stands within a tiny window. If instead it's possible to extend it all the way to 20 volts, like we have in our datasheet, making basically driving a GaN device as similar as possible to a silicon MOSFET. And in fact, even independent institutions like Virginia Tech have tested the gate robustness of IC GaN technology, which is the technology that CGD delivers to the market, to be 3 times more robust than a standard E-mode. I think that one beautiful thing of GaN is that it's lateral. That differentiates versus silicon and silicon carbide. And if it's lateral, why don't we exploit that by integrating what is needed to make it safer and more robust? And this is what we are demonstrating. At the end of the day, it's a matter, as I said before in the first part, it's a matter of breaking the perception. The perception by many customers and also by the general industry that GaN is coming late compared to silicon carbide, and therefore is still immature and cannot address easily some very demanding application. I made the example of the telecom. Telecom is quite challenging. It can be indoor telecom or outdoor telecom. And so there are precise requirements, at least 15 years lifetime, with a level of PPMs that go into the direction that Steven said before. And that is actually achieved by many by now, including CGD, and that can be demonstrated quite easily. So tackling reliability by providing proper test results, but also by exploiting the lateral nature of GaN, by embedding into the GaN transistor specific ICs that protect and extend the safe operating area of the GaN transistor is the direction that we have taken, and I think it's the direction that will be successful in future.
Thank you, Andrea. Let's move into silicon carbide. Pete.
Okay, yeah, thanks, Maurizio. So I kind of echo a lot of the sort of earlier points from the different speakers. I think the 2 areas that I would say, if you look at the sort of physical construction of a cascode FET, right, we sort of bypass the 2 sort of concerning reliability features of silicon carbide, right? We're making use of a silicon MOSFET, and we do things that it's standard in silicon, like we build in ESD clamping diodes into that gate and use that silicon gate oxide reliability that has decades of maturity and reliability built into it, right? The other sort of concerning area in silicon carbide is this phenomenon known as bipolar degradation, or so this VF drip whenever you inject minority carriers in a diode. If you look at the sort of cascode configuration, when you use the integral diode, you're actually conducting through a silicon 0.7 volt knee voltage, and then the series sort of in the reverse conduction of the JFET channel, right? And so there's never really any bipolar injection of any extent into the silicon carbide. So that those sort of 2 node concerns are sort of bypassed or mitigated with the cascode structure. So this is one area where we have some advantage. The other thing I would say is that, of course, we have to follow the same JEDEC and AEC sort of standards, and then go beyond it for application-specific tests. But one thing that none of us in wideband can get rid of is the fact that we're putting in a much higher power density in a much smaller die than our silicon sort of counterparts, right? And so power cycling is an area where I think the community has to understand what the life models are. And in fact, repeatedly, many different publications show that it's just not to the same level as silicon IGBT or MOSFET. And so we have to understand that and build that into sort of our application mission spaces, right? This is sort of a general area of need or growth and learning in wide bandgap. And then finally, I think the biggest issue is really educating the new sort of designers into when they are actually not operating where they think they are, right? And like I said, these are very small packages, very small die with very high power density, right? And so if you really want to exploit and try to cost out the smallest amount of semiconductor, well, then you're putting more burden into things like the cycling, and you're putting more burden into the thermal sort of management systems that you design beyond the die or beyond the package, right? And so that's sort of coming through education and continued education with the sort of designers.
Thank you, Pete. Thank you. And so back to GAN with Thierry, Vice Integration, and then Amitava, Tagore. Thierry,
Yes.
what about
Thank you.
reliability?
Thank you, Maurizio. So yes, GAN, as it was just said before, it's a lateral device, but also it's an heterojunction. So it's just not the same way than the vertical, the same failure mode than what we observe typically in a vertical silicon device or also a silicon carbide device. So what we do also at Wise Integration, we have a standard JEDEC 70 process. We also implement some specific tests of the AECQ. So we do probing, and we do also final test in order to sort our devices. And yes, but one point, it's a key point also, Andrea just talked about, it was the capability of GAN to be able to do some more integration, so more monolithically be able to integrate some specific function to be able to improve the reliability of the device, because it's for sure, if we compare to silicon or also silicon carbide, there is weakness on the gate. It's difficult to manage short circuits and surge currents. So thanks to this capability of the monolithical integration, we can manage this and we can make a more robust device. So this is also the strategy of Wise Integration, by integrating some over voltage solution, over current, also integrating some temperature sensor to be able to manage and to protect the GAN device directly with this integrated function. In terms of quality, because we talk about reliability, but in terms of quality, we do not yet sell the million of die, so it's difficult to say exactly how ppm failure we have. But what we observe, in fact, it's we follow all the rules of the semiconductor power industry. And also we observe that thanks to our various design-in we have today with customers, also GaN is switching very fast. So we need to manage inductance. We need to have the good package also to be able to avoid some failures. And also it's interesting to say that as it's working at very high switching frequency, we started to use it with a soft switching mode. So using this kind of soft switching mode, we can reduce the failure rate, but it's really dependent also about how you drive, how you control the GaN. So this is why using the digital control, we also can really manage the mode of failure, and we can prevent failure with the digital control in real time. So this is also a way for us to go to the improvement of the quality and the reliability of the system, of the device.
Thank you, Thierry. And now Amitava, Tagore.
So thank you for asking about the reliability, because that's really a very hot topic in wideband area, and I want to kind of highlight how we view the reliability. So first of all, the operational reliability, right? So how long the device will last, and it has been shown by various manufacturers of GaN that the GaN's useful lifetime is a lot longer than power MOS. But what GaN lacks is the field reliability, right? But all the calculations of accelerated lifetime and all those things show that the GaN has a much longer useful lifetime. So our view is there are really two main breakdown mechanism in GaN. This dynamic RDS(on) and then TDDB type of breakdown. So what we have to do is stick to a good process, number one. Number two, provide solid screening of defects at the probe and the final test. And then what we have to do, we have to show with accelerated test what is the useful life, right? You can use the Weibull distribution to calculate the useful life. And then you have to show or validate that useful life calculation through some dynamic HTOL. So we have to really do these 4 steps. Start with a good process, do an effective screening, then calculate the useful lifetime from accelerated testing, and then validate that using some kind of a dynamic HTOL. Now that's the operational reliability. There's another reliability is the transient reliability. And what we are finding, this GAN is quite robust. So there are three particular effects that I want to highlight in terms of the transient reliability. First is the gate protection. When first GAN came into into the arena, there are a lot of reports of breakdowns because of the transients. Now those things have been more or less solved, but what we find is the most useful is to have a monolithic driver, which gives a very clean waveform, and the transients on the gate is much better, and that gives you a lot of robustness against gate failures. That's number 1. Number 2 is the surge protection. GAN doesn't avalanche, whereas superjunction and silicon carbide, the avalanche. So essentially that is actually in a way is good, because what we find that the surge breakdown voltage in GAN is much higher than silicon and silicon carbide. So your protection circuits that you need to build will be much simpler. For example, GAN can easily withstand a surge of 1,000 volt, particularly the GAN that Tagore is using. In fact, what we found that our surge protection is even up to 1.4 kV. That simplifies many of this protection. So gate protection, surge protection, and third item is short circuit protection. GAN actually is a little weaker in short circuit protection. It cannot withstand short circuit as long as MOS and silicon carbide. So the approach that we are taking is that we are building monolithically various short circuit protection circuits on the GAN itself. So that will basically address the short circuit protection. So 3 items on the transient reliability: gate protection, surge protection, and short circuit protection.
Okay, thank you so much. Thank you. Nice topic. So we have just a few minutes before ending. So like last topic that I would like to share with you before the conclusion is so the classical question: what's next in terms of companies from each of you? So what are emerging trends? What new devices? What next long-term, short-term from industry, from each of you? But also, I guess Pete mentioned something about education. So I guess that there will be career developments in the future. We need to educate young people, students. We need to close the gap between university and industry, I guess, and just to involve more people to study power electronics instead computer science, maybe. So what's next? We can start with the order that I said earlier. Francesco.
So this is a quite interesting topic, actually, because it's a bit external and internal combination. I think all the university need to look at one special direction to educate and, let's say, help the students to think in a more complex way. Let me give you more details. Very often we have been seeing today, also in this short communication meeting, we have seen something like replacing traditional silicon MOSFET, but actually the gallium nitride, this is true for silicon carbide somehow, but for gallium nitride, this is a different story. What we need to look at is that the gallium nitride gives the possibility to go to a higher level of system in package. When we talk about system in package, we are not limiting to system on silicon. That means staying on one technology only. Here, we have the possibility to put together many different technologies. Here in ST, we are very proud because we have quite few proprietary technology. Actually, we are the company that in the market has the highest number of proprietary technologies. And here we can combine together motor control, ARM MCU, ARM-based MCU. We have sensing, MEMS sensing. So to give you a complex system in package where we can address different levels of know-how that should come from innovative education is to have a kind of sensing for motor control